And say I have a rotation associated with it. So I have omega associated with it. And that omega here is pointing up towards us. So this right-hand rule. So you got right-hand rule, thumb is sticking out of the plane. So all I'm seeing is the tip of the arrow, the tip of my thumb. Okay? So that is a positive value there. And say if I have a point P here, and I'll make it easy, we'll just do it at theta equals 0. So if I have P here, and let's say I have, well, let me call this P0. And let me call this one here P1. So I have two locations on that disk, P0 and P1. If I look at this velocity right here, if I'm moving like this velocity right here is going straight up. So that is the V0 tangential. All right? And that's simply equal to, that is equal to omega times the distance from the center, right? Now, at this position, P1, the tangential velocity, so I'm going to draw it like this here. Let me see if I can get the scale right. Is that the magnitude of P1? Is this the magnitude? Are they equal? Why is it greater? Yeah, it's further away from the center. So this is something like this right here. So this is V0 or V1t, which equals omega, the same omega, but times P1. And since the radial distance from the center to P1 is greater, the tangential velocity is greater. All right? So if you think of this right here, if I'm standing on a merry-go-round and I'm at P0 and the thing is rotating at a constant angular velocity, and if I step out like this, I go, I'm a little off balance. Do you know why that is? Because I'm moving faster, which means, what did I just do? I went from a V0 to a V1, which is what? Acceleration. And I have some mass. So mass times acceleration, I feel like a jerk or a force associated with that. That's the Coriolis acceleration from a physical perspective. All right? Now, the Coriolis acceleration, I mean, I used to cover this where you can look at, in fact, I think I still have the notes of it. You know what hurricane it is? Katrina. Katrina's over here, right? Hugo. There's Hugo. In 89? Anyway, the Coriolis is going on in a big way here. All right? And so what's happening is you got a low pressure here, and as you're moving out, the Coriolis acceleration is changing. And what that does, as the air is rushing in, the Coriolis acceleration is changing, which causes it to spin like this. So that's when and why hurricanes, when they're coming from the equator and they hit the United States, normally they spin like a wheel, and there's friction here. And they feel that friction, and nature doesn't like that friction, and so it just kind of spins, and it acts like a wheel, and usually it goes up the coast unless there's enough momentum to shoot inland. All right? But it's all based on the Coriolis acceleration. And the low pressure and the wind, or the air mass moving in towards the center of that low pressure system. Okay? So that's another example of Coriolis acceleration. One that we use as from a mechanical engineering perspective. You know those rainbird impact sprinkler heads that go and then go. That's the Coriolis acceleration in action. Because what's happening is that hammer, as it's going out, it's experiencing a force that is being influenced by the Coriolis acceleration. And that's why the thing spins. Okay? All right, so let's look at the direction influence a little bit more. So if I have this disk here, and I have a slot, and I have this puck here, or this ball bearing or whatever in the slot. If it's moving this way, that's a positive slip velocity. If it's moving this way towards the center, that's a negative slip velocity. All right? And we also know that if we have omega going like this, that means we're seeing the tip of the arrow, and that is a positive value. So that's a plus omega. But if omega is moving the other way, therefore we're seeing the tail feathers of the arrow, then this is a minus omega. Okay? And so really all of these things here are vectors. So let me put lines on them. And the Coriolis, from what we saw earlier, right here, is 2 omega crossed into P dot. So it's 2 omega crossed into P dot. That gives us the direction influence of the Coriolis effect, or the Coriolis acceleration. So let's take, there's 4 examples of this. So if I have my omega being negative, so I have a negative omega here, so I'm seeing the tail feathers of the arrow. And I have a positive P dot, so I have a plus P dot. And I cross omega into P dot, so here's the blue pen. So I'm looking at the back end of the pen, and here is P dot. So if I cross this into this, see how my thumb is pointing down and perpendicular to this? So therefore, my Coriolis will be like that. Yep, sure can. So here's this pen, and it's pointing into the screen. Okay? So the pen's pointing into the screen. I have P dot kind of pointing up at like a 45-degree angle or something. Using the right-hand rule, I'm going to cross this pen into the red pen, because this is P dot, so omega into P dot. So when I do that, when I cross this into here, I get my thumb sticking down, and it's, all these things are at 90 degrees from each other. Okay? Does that make sense?
Is that symbol with the circle to X, is that to represent the negative right-hand rule?
It is. It's to represent the tail feathers of an arrow. Okay, so we're looking at the tail feathers of the arrow. Okay? As opposed to the pointy, sharp end of the arrow. All right? So if we go ahead and look at say the positive omega. So we got positive omega, and we have a positive p dot. So when I do this, now I got a positive omega, I got a positive p dot. Right-hand rule, when I cross this into here, now my thumb is sticking up. So this right here is AP Coriolis when I have a positive p dot and a positive omega. Then the other two are, if I have a negative omega again, and I have a negative p dot this time. Okay. So now, if I look at the tail feathers here, and p dot is like this, so now I have this situation right here. So when I cross this into here, my thumb is sticking up like that. So therefore, your AP Coriolis looks like that. Again, all these are 90 degrees. So the last case here is looking at a positive omega and a negative p dot. So on this one here, if I get the pointy end coming out at me, and I get p dot like that, right-hand rule, if I cross this into here, my thumb is sticking down. So your Coriolis, AP Coriolis on that. All right? So that's important when we solve these problems. That's why I'm going over. Okay? So what I'm going to do now is a couple of examples. All right, so here's a word problem. You got a merry-go-round. Rotating